All right, so I wanted to talk to you about science, like coding like a hacker in a science way. Oh, okay. Well, I want to tell most of you. Okay. Okay. So I want to tell you about good coding practices, but also bad coding practices. So there's kind of well, the hacker way of doing things is like whatever you can do to get stuff to work is the right way to do it. Then there's writing shareable code, which involves many of the things that Yark talked about and many of the things that I'll also tell you about. But for the purposes of hackathons this week and for kind of writing quick things in your life beyond this week, the main thing in terms of thinking like a hacker is just get it to work. Don't worry about the rules or the right way to do things. If it works, it's good. So the pipeline for doing that is always start with a GitHub repository. It's really easy to make a new one. So you log into GitHub, make a new repository, name it something. And then just the only thing you have to do is just commit and push your changes insanely frequently. So when I am starting a new hacky style project, I'll just like every minute or two, I'll just do a commit. And if you push it to the repository, that means you're getting work done and doesn't matter what it is. And then you have a log and it seems like you've committed hundreds of times and it's so satisfying. And it encourages an exploratory approach to coding. So you write a line, you commit. You write another line, you commit. Then you realize that line you just wrote is stupid, you uncommit. Then you realize it was good, you commit back. I love that pipeline of just going back and forth through time with GitHub. OK, that's really the key. Second, other people may have solved parts of your problem for you. And they may have come up with elegant solutions or messy solutions. But if they came up with working solutions, that's the important thing. Copy them and get your thing working. But in the spirit of being kind of a good citizen, cite your sources. So what I usually do when I'm kind of starting one of these hack together projects is you insert a comment with the web address of the thing you copied from. And that reminds you later to do the right thing and cite them if it ever turns into a paper. Right. Then, once you have a complete working draft of your code, messy as it is, then it's time to really test it. And testing means trying to break your code. So you might have thought of a silly one application of your code, silly or not. Then you think about, OK, well, what if you were trying to create this, do this analysis or run this program in some extreme case? What are the edge cases of your particular problem? Does your code work for those edge cases? Or what if someone were to take your software package and try to solve a totally different problem? So you wrote a software package to analyze brain data. What if someone wants to use some other time series data, like stock market prices or any sort of, really, any time series, weather patterns over time, anything? Would your code need to change? Does your current code support it? What data formats are required for those other applications? And then you don't have to support every possible case, and you don't have to, but you just have to think about what cases do I want to support. Make sure your code supports the ones you want to support. And then the next step is to create a tag, or it's called a release on GitHub. And the first tag that I make is always kind of a messy, terrible version of the code that is like a minimum viable working product. And then you begin the cleaning process, which is what I want to talk about for the rest of this presentation. But probably for this week, all you'll be doing is, and maybe not even getting this far, just creating a minimum viable product of some hacked together analysis or what will eventually become an installable package. Okay, does that make sense? Any questions on that? Okay, so there are really no rules or structure to that style. But if you want to share your code, which we all do, because we're open science people, then there's other stuff we have to think about. And it's good to think about it anyway, even as you're doing the kind of hacker-style approach, because maybe there are going to be equally easy alternatives that you could pursue, and just having the kind of good way to do things in mind as you're going might guide. OK. So there are a bunch of kind of tips that I've compiled over my 20-something years of coding that I thought I could impart onto you. OK. So the first is simplicity. My favorite definition of simplicity is it's the art of maximizing the amount of work not done. And the way to implement this in practice is to ask at each step of the way, as you're writing your code, what is the simplest way I could approach this part of the project? Which means, how can I maximize the amount that I'm not doing? It's not always easy to see the simplest way, and so it's often helpful to start with the messy, hacked together, terrible solution that takes forever to run, and then go back and think about how can you clean it up? How can you write it in 3 lines instead of a gazillion lines? And it's not only nice for other people reading your code, but it's nice when you go back to your code in 10 years and realize that it's unreadable. If it's unreadable, you won't be able to use your old work. If it's simple and clean and readable, then you'll be able to reuse your own work without reinventing things. OK. So more concretely, one principle of simplicity is to try as best as you can to write everything once. If you have a particular function that's used multiple times, try to design your code so that you only write it once. It should appear in a single place. If you find yourself copying or replicating structure, that means you are not writing simple code. So carve out that thing into a function and call it multiple times. OK, and that relates to modular programming, which I'll talk about next. Second, you may want to support many formats in your analysis. But if you were to support each of those formats in their own function, that would involve replicating. And you don't want to do that, because that would result in messy, not simple code. And so there's another principle called funneling. And that basically involves consolidating all of your data formats at the very beginning into the format that you'll use from that point on in your code. And that allows you to write simpler code. A third general strategy is to fail fast before you've wasted your or the user's time. So you don't have to support every use case or every possible input. But before you do the long parts of your analyses, you should do checks at the beginning of your functions and the beginning of your code so that you try to guess, is this going to be supported, in which case you continue, even if it takes a long time, or is it going to fail, in which case you want to do that instantly if possible before you've run the complicated steps. Fourth, think about who's going to be using your code. And your users are always lazy, just like you're lazy when you use other people's code. And that means if you want someone to use your software package, make it easy for them to use it. So set sensible defaults. Keep your syntax and design clean and consistent, free from clutter. Don't make them type commands that are replicated from time to time when they use it. And finally, even though we want our analyses to run quickly, it's often better, I've found, to write simple code than fast code. except in some edge cases. But it's at least almost always the case. So the elegant, slow solution is often preferable to the optimal, complicated, fast solution. Okay, but I'll also touch on optimization. So any questions on those, or any comments or concerns, disagreements? You can disagree. Okay, nothing. Okay. Modular programming is a really powerful technique. The analogy that I like is like building with Lego blocks. So you can imagine each part of your code is like a little Lego block, and then you want to construct new blocks that can in turn be built into more complicated structures, which can in turn be combined into even more complicated structures. But in order to, so the thing to think about as you're writing your code is to figure out what are the fundamental modules that I'm going to want to build with, and then what are the modules that are going to be built from those modules, and you kind of get more and more complicated. And so your final top-level program is going to be a very simple, clean set of commands or calls to each of your modules. And those modules are going to be, in turn, clean, simple calls to other modules until you get to the lowest level thing, which is usually the messiest part that actually kind of does the stuff. Okay. Basically, when you're reading really clean code, it kind of looks like you're reading a informal description of an algorithm rather than reading Python code. Most of the stuff, the details, is abstracted away from, when you read really good code. Also, in the interest of not replicating code, modular programming really helps with that. So you write your module once, and you reuse it many times rather than pasting the same or similar code many times. Right. Oh, right. Also, writing modular code facilitates optimization. So if all of your modules call one function, then speeding up that function is going to improve your whole code. So you just change one thing, and that makes everything faster. Whereas if you've replicated structure a bunch of times, then making your code faster means going into each of those replicated structures and optimizing all of them. And that's often painful. So to keep your life simple, make sure that each thing is just written once. Okay. Right. Sometimes it's not directly you find yourself in a situation where you're well, I'm not doing exactly the same thing multiple times. I'm changing some little thing. And so there's kind of an art to figuring out when you even have replicated structure. And I don't know, I often find that I'll write kind of multiple functions that do sort of similar things. And in the process of writing the second function or the third function or the fourth function, I'll realize, there's a general solution to this. So by adding some arguments, I could write a general purpose function that solves all of these problems in a similar way. And that allows you to reuse code. Okay. Okay, any questions on modular programming? Okay. Just jump in with questions as they go. Okay. When you're packaging up your code, it's important to consider the scope of your package. So often people ask, what problems is my software package solving? But just as important is to think about the problems that your software package is not solving. So you don't have to solve everything. You just have to solve the specific set of things that you set out to solve, and then fail fast if a user tries to use your code in an unexpected or unsupported way. Also, the fact that you don't support some use case in your first version of the code doesn't mean that you can never support it. It just means that you're not supporting it in the first version of your code. That's it. And it can evolve over time what you support and And that's great. When you kind of construct a software package, it's often helpful to keep your files and folders organized in as flat of a hierarchy as possible. And I'll talk a little bit about that. And the whole point is that you want to make it easier for you to develop your software, you and others to maintain your software, and for other people to use your software, and also to modify your software for their own purposes, to make better tools that you can then steal back and use to do even cooler things. And that's how science happens. OK. So it's great. Yes. Yeah.
It sounds like what you're saying is that you think about writing modular code that can be reused maybe across different data sets or across different analyses. So one thing I always struggle with conceptualizing is what pieces of the analysis code live just with one project, and which pieces should be extracted into something that's project or domain general.
Yeah, it's a great question. If there's maybe you have a concrete example. It's very general.
Sure. So like,
yeah.
I do human imaging work, and or let's make it a more simple example. Like, let's say you need to run a t-test and you need to report a Cohen's d statistic. So maybe you write a function that takes the input and computes your Cohen's d, and you know that every time you run a t-test in every project ever, right, you're going to need to report that Cohen's d. But specifically reporting the Cohen's d for data set A only happens for data set A, and it only happens for data set B. So the code that computes the Cohen's d like lives in this modular place, but the code that computes the Cohen's d for data set A and for data set B, does that also, like, is there a domain general package and then a data set A package, or is there just like analysis scripts that call that?
I guess in asking your question, I think you're thinking about it in the right way. So you want to probably have some general purpose package that takes in data and returns whatever statistical values you want. And that might be called by each of your sub-projects in whatever, so maybe there's project-specific data wrangling that needs to happen. And that might not be generalizable across projects. But once you wrangle your data, then you want to call some common function. So like, let's say you made an error in how you computed something. That's going to mess up all your projects. But you want to fix just one thing, not fix everything, every project you've ever written. So that's also kind of an example of how modular designs can facilitate code maintenance, because you want to basically minimize work for yourself. Yeah, good question.
Also, a nice example of funneling too, where all your data things might have different functions that happen, and you get into the same thing where your functions don't work. And then we do it different ways. So we have like a lab toolbox that we'll use for a Cohen's d function. So we have that, and it works with a certain type of data. But then sometimes we make packages that just work with the data set. So there might be functions that you're only going to use, but because we work with this data set over and over and over again, they get reused and other people might be using it. So we might make a package that's just for that data set that won't generalize to the data sets. It just kind of depends on your.
And that package might live separate from the analysis code. So like your analysis code calls that data sets package and the
exactly. So like in the project folder, we might have like a code one that has all your scripts, which might be Jupyter notebooks or whatever MATLAB scripts or whatever. And then they're going to be importing the packages that have the functions they're going to use it and then using them. So you have one that's kind of like, I think the better the code you write, is kind of Jeremy's getting at, the easier it should be to read. So if you have a script that does everything at once, you read it, you're like, I have no idea what any of this is doing. But if you have one that's like doing everything, so you get the concept of what it's doing because it's calling some function that knows how to do it, then your scripts end up being like a couple lines of code to do everything. They're much more readable, easy to figure out what you're doing, and it's way easier to maintain, which is what Jeremy's advocating.
So many of you have done complicated analyses of multiple projects, and I know I've encountered the scenario, and I guess many of you have, where you like figure out some solution to a non-trivial problem, and then you have to resolve it in another project, and it's like the same solution. So the kind of lazy and ultimately more like the solution that makes more work for yourself later is to just copy your old code or like copy it and then tweak it a little bit. But the modular approach would be write a separate package for doing that thing that will be generalizable across your different projects, and then just write it once. And then, when you have to do the same thing in 10 more projects, you don't have to write it 10 more times.
I think the tough part, especially when you're just starting, is knowing when, on the one hand, I'm not going to name names here, but you could build that whole package the first time you're going to do it, spend 3 weeks doing it, and then realize that was the analysis you went to run in the first place. And had you just like done this like quick prototyping, you would have realized that you had not spent 3 weeks doing it. So that would be too early. But then you don't want to do it like copy and paste it like 5 times or 10 times. So kind of knowing when you realize it's going to be a general problem.
Yeah, my favorite thing to do is start with the hacker approach, get some minimum viable product working, and that's when when you get the set of graphs that you think you want or the set of functions that you think you want, then it's time to turn it into a clean software package. Before you have that minimum viable product, it's too early to go into this like code cleaning phase, because we've all written code that we throw away, the next day and then just never return to. Okay. Cool. So if you're going to use your code a lot, that's when it's worth simplifying and cleaning it up. If you're going to be sharing your code, that's when it's worth simplifying and cleaning it up. If you think you're going to visit your code later, simple and clean is good. But if you're just doing something once, then it's like simple and clean is not necessary. It just whatever works. So that's kind of the guideline that I use. Okay. Cool. Okay. So if your code is kind of tied up into a nice package, it's going to be used more. You're going to be more famous. Future you will think past you. Temporal loops are a big theme this year, I guess. Yeah. You can bootstrap off of nice, clean code. So an old package might serve as a baseline or a module for a new package, and you can kind of write quicker and quicker and faster and more complicated with each new project by calling old packages. Also, we want our science to be like as correct as we can make it. And if you spent a long time writing a nice clean software package, then it's more likely to be free from obvious errors than if you're kind of redoing everything in a hacked, messy way each time. Okay. So the pipeline that I use, and everyone has their own preferred pipeline, but I really like Jupyter Lab, and I use Jupyter Lab to kind of get the basic functions in place. So you like open up a Jupyter Lab session and just start plugging in code, and it's often super messy, but it's organized, and like I'm committing to GitHub like every cell. Then once you have the Jupyter Lab notebook or the IPython notebook done, you've got your basic functionality in place, then my favorite development environment for like turning things into packages is PyCharm. So, and I also like Atom, which is kind of a lightweight editor that has a lot of nice plugins. But PyCharm in particular has a lot of built-in functionality for helping you to make packages that are correct. So it's really too many features to list, but it's got some of the like really awesome ones are it allows you to refactor your code, which means you can change a variable name or a function name, and it will search all your files throughout all your project and rename that variable or that function, and it is able to distinguish, like, based on the scope of the variables, which things to actually rename and which things not. So if you have like a variable named x it won't rename, it won't just do a simple find and replace. It'll say like, okay, based on how Python code works, I'll only rename these instances of X that you meant to rename. It's also got a beautiful debugger that Lucy touched on, but it's like a graphical way of stepping through your code, and you can peek at all the values of all the variables and have ultimate control over the execution flow of your program. And it's very similar to the MATLAB debugger if you guys are MATLAB programmers. It also has Git integration, so you can like select which files to add to your Git repository or ignore. A nice profiler, so you can figure out how long each part of your code takes to run. And even though it's a closed source and non-free in the strictest sense software package, it is free for academic use. So with an EDU address, you can get a free license very easily. So it's free cost-wise. Free as in beer. OK. I also like using Atom. And the main thing I use Atom for is collaborative coding. So if multiple people want to work on the same file, which I imagine will happen in the hackathon sessions this week, one of the Atom plugins like allows one person to like click a button, and that sets up a server, and then it creates a like unique ID code that anyone else can log into, and then everyone can edit the same file. Kind of like Google Docs and Collaboratory, but you can run it on your computer, which allows you finer control over what packages are available and that sort of thing. OK. Finally, once you've got kind of the basic software package and all your files in place, then I go back to Jupyter Lab, and then I kind of use that to run tests. So I'll have my like hacked starting version of my Jupyter Lab notebook. Then I'll write a package. Then I'll install it on my computer. And then I'll kind of try to replicate my original results using the kind of library that I've written. I find that works really well. OK. Any questions on that? Yeah. The key is really there are many tools out there. There are many ways to write code. And I just encourage you to make use of whatever ones you like and be flexible and switch back and forth. Yeah.
This sort of specific question about debugging. So
yeah.
Let's say you're like making a class for a package or something like that. Now, are you running your debugger on a test that you've written to use the class, or are you debugging the actual class source, or how are you? What's your workflow there?
So usually in the initial kind of hack together Jupyter Lab, there's some data set or fake data set that I'm analyzing. I guess it's project specific how like the debugging proceeds, but one way of debugging is to kind of bypass the PyCharm debugger and then get your basic analysis working. Writing the package just is basically pasting in functions from your original Jupyter notebook. And then you just call those functions from your cleaned up Jupyter notebook, and it should return the same results. And that's kind of a simple sanity check. The reason I like developing in PyCharm is the debugger is very powerful in terms of how it lets you kind of drill into code and run one line or drill into a function even deeper. And that functionality just isn't easy to access in Jupyter notebooks. There's a like command line debugger in Jupyter notebooks, but it's much, much harder to use. And so in my view, there's just no comparison in terms of how powerful the debuggers are. It's way easier to develop in PyCharm, and if you have like serious debugging to do. OK. Luke mentioned that people are fanatical about Python syntax, and I am also fanatical about Python syntax. There's a correct syntax, and it's called PEP8, and here's the website. It defines very specifically how to do things. I actually don't think it's important to adhere 100% to PEP8. You should check out this link. It's just enthralling. Really, really awesome. OK, but the main thing is you want to be consistent with each type of named object. So a variable should always be represented by the same style of name. A function should always be represented by the same style of name. A constant should always be represented by the same style of name, et cetera. And I'll get more specific about what I mean by style of name. It'll make your code easier to read at a glance, because once you know what styles you've used for different types of named objects, you can just quickly know, OK, this is a function, this is a variable, this is a loop iterator. And it makes your code easier to read. Also, really helpful to making your code easier to read is adding spaces around operators. So does everyone know what this line does? Increments a by the product of b times c. Spaces are key. Makes it very much easier to read if this is embedded in, like, well, any other lines, really. OK. Also, keep your code visually clean by truncating your lines at some small number of characters. And then you want to group related lines and then kind of leave extra space between them. And your whole goal is to maximize readability at a glance. Also, there's a tendency of beginning coders to really go crazy with comments. And in my view, if you write clean, simple code, you really shouldn't use comments that much. If you've kind of named your variables well and you've followed simple modular coding practices, then your code is itself a comment. It's really only for kind of tricky one-liners that are not immediately obvious that comments come in handy. OK. Here are the naming styles that you should consider. OK. So a loop iterator is represented by a single lowercase letter. OK? Or like minor scalar variables. OK. If you have a constant or a matrix, single uppercase letter. Variables are either lowercase or lowercase separated by underscores. I usually reserve uppercase things for like constants or global variables, even though those are messy and frowned on. Camel case, which looks like this, is for classes. And then these should never be used. Why? It does not. It doesn't conform to PEP 8. It just, your code won't be. Your code, I won't run your code. No. The main important thing in seriousness is consistency. So if your favorite thing to do is to write capitalized words with underscores, then go for it. But I've found that code looks a lot cleaner if you conform to these standards. Mixing cases looks messy, but for classes it seems to work. It's not ideal, but it's a nice way of distinguishing between classes and other types of variables, but you don't want to go crazy. So it's like if you've ever seen a web page with like 10 fonts versus like 1 or 2 fonts, looks a lot cleaner to have a small number of fonts. Or like a science poster at SFN, if someone uses like 30 colors and every section is like a different font size and a different color, it looks visually messy. If all the fonts are consistent and all the colors are clean and nice, it looks nice. So the main thing is to think about how you're going to be consistent and just stick with it. And here is the kind of, well, it's the official Python way to name variables, but just be consistent is the main thing. And all else being equal, you should choose this way because it's the best. OK. Here's some messy code. You can kind of see, like, let's see. what have I done? So many comments, right? The spacing is a mess. No spaces between operators, right? All it's doing is just adding the different entries of this vector my data. And here's a much nicer version that is the same code, but just like adhering to that naming convention. This is so much simpler to read. Future you will thank you. OK. Good? OK. Funneling is a super powerful programming principle. So suppose you want to do an analysis. I mean, we will do this week. You might want to do an analysis on fMRI data or EEG data or ECOG data or spike rate data. But each of these different data types come in their own formats. But the underlying analysis that you want to run might be common. So the idea of funneling is support whatever you want, but be predictable about the output of the kind of initial formatting steps. So you might want to check the data types or the format types or the file extensions of the inputs, and then do some initial processing step at the beginning that supports all your intended use cases. And what comes out of those initial processing steps is a single data object that's formatted in one predictable way. That means that later on in your code, you don't have to keep checking for data types. You just operate on the single data format that you know will appear everywhere else in your code. In addition to reducing the amount of stuff you have to do later on in your code, it also allows you to easily support new data types without changing anything in your code except that initial funneling step. Like if you want to add support for MEG data, well, add that to your kind of data formatting function, and then everything else in your code should continue to work. OK. Make sense? OK. So you shouldn't, so when do you need to funnel? If you're doing any checking of the data types of your variables or the file extension of your inputs, then you need to funnel. And it should just be done once at the very beginning of your function, and only in functions that the user interacts with directly. So if you have some internal function, only support one data format, which is the format that your whole package uses internally. Anything the user interacts with, they might give you data in whatever format, and then you'll kind of go through the formatting step. Does that make sense? OK. Right. The internal functions that your package relies on that the user doesn't see, they effectively become pre-funneled. You know the format of the input, and you don't have to check the input types. It'll save time and effort, et cetera. OK. So here's like a silly example. But suppose you had a function brain plotter, and you want to support many different types of brain data, with some arguments. Then the way this will work is format data will take in whatever data types the user passes in. And the idea is you'll write this function to return a predictable new data object with whatever options you have. So if you have like default arguments you want to fill in, or you want to like read data in different ways depending on the format, then this format data function should be written to deal with all those scenarios you want to support or error quickly. And by the time you get to this line of your code, you know what format these two variables are in. And so you don't have to do any checking at all in your analysis functions. And it will make your life way easier. And then you just call your plot function on whatever your analysis returns. And again, you know this data format. So your plot function doesn't have to check data types or anything like that. It just knows what format it has to support. It's one format, and that's it. Yes?
So is it like better to do it every time you're running like a new function, or for instance, because like for instance, reading and writing that takes a long time. So what I do right now is everything is in MATLAB. Like I save the prompt and like I know dimensions and everything. I have the new like saved versions. I just use that for everything.
Yeah, so there's a difference between like pre-processing and funneling. So pre-processing steps that take a really long time can be done outside of any given function. So in your
This is like, I don't mean pre-processing, I'm just like reading a nifty file in MATLAB, it takes time. But reading a mat file is fast.
I guess I would call changing a nifty file to a mat file one of your pre-processing steps. So pre-processing can involve changing the values of the, in fMRI data of the voxels, or it can involve changing the format type. And I think it's totally fine to have some step that takes your raw images from the scanner, processes them, does whatever you want to them to change the format into something convenient, and returns, and creates a folder of MATLAB or like .mat files with one file per subject, smoothed and aligned and all that. And then your Python analysis can, or your MATLAB analysis can just read in that folder. That's totally legit.
So what are like the other examples of like funneling? Like for instance, like I don't know, ROI?
Well, suppose that data, one example would be data might be a .mat file or a raw nifty file. So if it's a .mat file, maybe you want to read in a particular variable from that file. If it's a nifty file, maybe you want to convert it to a 2D matrix. If it's a NumPy array, maybe you want to leave it unchanged. If it's a pandas data frame, maybe you want to read out the appropriate columns and indices and return that as a NumPy array. So you can imagine all of these different data formats might be returned as a single format that is supported later on. And it doesn't matter what that format is, it just has to be something that is easy for you to support later on. And then later, suppose you wanted to add support for some like other format, like you've got a new EEG system and it has some weird format that it outputs to. All you have to do is add some code to your format data function and make sure it returns like a NumPy array of, two-dimensional NumPy array, and then everything else in your code should continue to work. Okay.
What is the difference between funneling and munging?
And what?
Like data munging.
Data munging. I guess, so I often think of data munging as a pre-processing step. So you might have a gazillion files made in your experiment and like multiple nifty files per subject or whatever. Maybe they're like not smoothed or aligned, and everything, you want to align things across subjects spatially and temporally. Some people were data was collected in one format, some people in another format. So when you're like sharing your data set, you might want to munge it by like putting everything into a common format, some simple format that you decide on. Funneling means the format you decide on and the format that someone else decides on that you want to still support would be still able to kind of be processed by your analysis script. Okay. Another tricky thing is to know when to split different things. So I said earlier that it's nice to have as flat a hierarchy in terms of how you organize files and folders as possible. So why not just write everything on a single line? That would be the flattest hierarchy, right? Okay. Well, that's going to be messy to read, so you don't want to do that. Plus, unless it's just a short line, well, unless it's a short line, it's going to be a long line. Right. Okay. So you split a line when you have too many characters on that line. That's simple. That's just PEP 8. You're all going to read that, right? It's very exciting. Okay. Lines should be grouped together. like without an extra space between them, if they are conceptually or syntactically related. So your import statements at the beginning of your file, or like a group of lines performing some function on similar data, et cetera, or a similar state of the data, something like that. Those all get grouped together. And then to visually separate them, you add a double space. Okay. Now, if the group of lines is going to be used by another function, then you don't want to replicate those lines, so you have to carve it out into a separate function. So that's when you know to separate lines into a separate function, if they're going to be reused. When do you make things a separate file? Well, if you have multiple functions that are not thematically related, or that could be grouped into subthemes, then you may want to separate them into different files. So if you have 3 functions that do very different things and they're all short, that might be OK to keep in a file. But if you have like 100 functions that do 3 types of things, you might want to group them into little smaller groups, each in their own file. And the kind of rule of thumb that I use is you want to keep each file about a page long, like a 8.5 by 11 size 12 font Times New Roman, doubles, like all the things we tell our undergrads. That's the, it's not a character count, but it's an approximation. You don't want to just create a ton of small files, each with like a tiny amount of code, or one super, super long file with like every piece of code you've ever written in it. And then folders are kind of used sparingly. But if you've got a big package with lots of different files that are themselves thematically groupable, then folders might be a good thing to use. OK, make sense? It's all what you think looks right, but that's the kind of general guidelines that I use. OK. I think this is one of the last things. Storyboarding is how you figure out how your code is going to be used. Okay. So when you're taking like a systems design or algorithms design class like as a computer science major, that's when you learn about storyboards. And the idea is you want to describe user stories about different intended use cases. So conceptually, you try to imagine, like, why is the user here, and what are they trying to do? How did they get to this point running your code? And thinking in this way helps to enforce a user-centric mindset as you're developing. And then the stories that you support defines the scope of your project, and also the set of test cases that you're going to need to check to make sure if the users are using your code in the way that these stories describe, that's what you need to test. You want to make sure they work. And then be really specific in your stories. I'll give some examples. If your story is too general, then it's not going to be helpful. And if a particular use case you're imagining doesn't apply to a given story, then you either need a new story or it's outside the scope of your project. OK. So here are some examples. A favorite thing in computer science is to name people alphabetically and in alternating genders. Anyways, Alice is a neurologist with a collection of structural MRI images. OK, so what does this tell us? This sentence is important because it tells us about one data format we're going to have to support. What data formats might MRI images come in? Well, we're going to have to come up with a list and decide which ones we want to support, which ones we don't want to support, document that somewhere. Okay. She wants to create detailed images to help her visually identify potential anatomical anomalies in her patients' brains. Okay. So we're going to have to plot some sort of high-resolution image. Okay. I don't need to read through each of these, but you want to define how does the data come in, and what is the user trying to do, and make a new story out of each thing that you want them to do. Okay. Any questions on that? I don't know if this is an intuitive way of thinking about software design, but it's a nice user-centric way of thinking about software design. Okay. Any questions on that? No. Yes.
Just to make sure that that's like not minimized.
Yeah.
You'll notice that when you use certain packages, they're like really easy and intuitive, and you can kind of just get used to it, and it kind of has everything you want and nothing that you don't, that you know of. And then those you don't even notice you're using, you just use them, and they're like, oh, this is wow. Until you use one that's like written by me, and it's like completely has no idea. Either it's like really complicated, you don't understand why there's all these use cases or how to use it and all this stuff, and you have to read the manual like 50,000 times and go back and forth. Basically, like good design means it's way more fun to use and easier, but it's really hard to do, I think, in general. And a lot of times it needs to be refactored a lot. So you start using it, this doesn't quite work. We should find a way to simplify this, or this is awkward. And you can't think of that ahead of time. A lot of times you kind of have to keep redoing it. And I think the storyboarding idea, I think, is interesting as a way to kind of think about the use cases ahead of time about how you might want to use it, which might change the whole design of how you're going to outline your package. But anyways, I think it's a really underappreciated thing in software development.
Yeah, often we think about, we write code as scientists in the lab for ourselves or our bosses, and then we might share an analysis to like satisfy, like do something minimal to be like a good open scientist, or someone asks for our code and so we share it with another lab member or collaborator or something like that. But that's not going to get you like clicks or downloads. To get other people actually using your tool, it's got to be easy for them to use. It has to support the scenario that they're trying to use it for. And that the easiest way to do that is by thinking about like putting yourself into the user's shoes and saying, here's who I want to use my code, and here's how I want them to use it. And if I imagine myself as them, what would I do? And then that use case should work easily, simply, intuitively, without knowing all the inner workings of your analysis or your code. Okay. Testing is important. The general rule of thumb in terms of what you want to test in your code is that if you've written storyboards, you want to test each storyboard and recommended use case of your code. If you add a new use case or new storyboard, then you want to add new tests. Also, after you've gotten your kind of minimum viable hacker prototype product, and you start to put together your toolbox more formally and clean up your code, that is the time to start writing tests. Even though it adds a little bit of work from the start, it will make your life much easier in the long run. It's much easier to like write a function, write a simple test for it, write another function, write a simple test for it, than to like write your full toolbox and then go back and think about, okay, what needs to be tested? It'll just take a lot longer. Because at the time you write your test, you're already in the mindset of writing your function. So writing a test is just part of writing new code. Okay. Also, it's often useful to generate some sample data and then just make sure your tests run on the sample data. So you know the answers, see that you get those answers. PyTest and Travis are two, well, Travis uses PyTest, but these are kind of nice Python tools for doing tests, and they can be hooked in with GitHub so that they run automatically when you make a GitHub push. They're particularly nice, but they're beyond the scope of my remarks today. But happy to talk about them offline. Okay. I think we're nearing the end. Debugging. Another useful thing. How do you fix your code when it's broken? The general strategy is to section out the thing you're trying to fix and make it easy and fast for yourself to run it. So you want to get to that point in the execution pipeline of your program as quickly and easily as possible. If you have a huge data set that takes an hour to churn through, and then the next line is the thing that's broken, that will take a really long time to debug. we've probably all been there with our code. But that's not an efficient way to debug. The efficient way to debug is to make a small test data set that your analysis can run on really, really quickly. So you press your debug start thing, churns through it in a second, and gets to your line that's broken. And that's the mindset you should have. Also, you want to set up scripts and your scripts so that you don't have to retype everything each time you want to run that same line again. So if you're finding yourself typing like 3 or 4 lines each time you want to get to the point in your program, that it's going to be way faster for yourself to write a script that can just get you there quickly. Right, especially if you're running the same line like hundreds and hundreds of times. That's a lot of typing. And then another kind of useful tip is, even though your bug might have appeared in some complicated version of your analysis, try to carve out the simplest place where that bug shows up, and that's what you want to start with. Okay. There are different debugging tools that are great. Jupyter notebooks are really useful for rapid, kind of quick and dirty debugging. So a setup that works well is to kind of have all your import statements, and then you want to use one cell to kind of initialize and reset your workspace, then define the thing that you want to debug in a second cell, and then in a third cell, run the function and display the results. And then what that lets you do is just restart your kernel, rerun everything, like run A to load in your data, then interact with it. Run B to define your function, make sure there's no problems defining your function. Then run C, and that's what actually does your analysis. And basically debugging is just like fixing cell C. Okay, that's a quick way to debug. Does that make sense? Okay, and then if you have really anything more complicated than a simple sort of one-liner debug problem, then you want to use PyCharm. There's a tutorial that I've linked to really get into the nitty-gritties of the PyCharm debugger. But Lucy showed a demo where you can kind of set up breakpoints in your code, and then the code executes up to there. You can interact with it, view all of your variables, and jump in and out of different functions interactively. And it just, you can go to this part of your code, copy in the next few lines, and they're all broken, and then you fix them, and it doesn't crash or harm the rest of what you've written, and then you can kind of get the right code without rerunning everything and paste it in, and it's really quick. Okay. All right. Finally, I think this is the end, almost the end. Okay. Optimizing is making your code run faster, which is often key to scaling up your analysis to work on bigger data sets. But you shouldn't optimize too soon. The things you should optimize are functions that will run many times. If you have a line of your code that runs a gazillion times, making it just 1 millisecond faster will still make your whole analysis run a lot faster. Right, and then if you have a function that controls some real-time thing, or that would be inconvenient to run a long time, those are also good targets for optimization. Or if the user is going to interact directly with it, like importing a library, that should be quick. Showing a plot, that should be quick. Those are good things to optimize. How you optimize is tricky, but the idea is you want to go back to thinking about how you can reduce redundancy. So any computation that's done multiple times, that's a point where you need to optimize, or you should optimize. If any, you could pre-compute those values and create some lookup table, eliminate steps that are unnecessary to do multiple times. Often it's hard to do it, but the kind of real thing you're doing is you're trying to think about how exactly, like which specific set of instructions are being executed on the processor, in what order, and how does changing my code affect the order that things are run on the processor, and you're trying to optimize that. So thinking of things like drilling down to that level, like will solve all of your optimization problems, but often you don't have to drill down that far because fixing higher level problems just makes it fast enough. Okay. Also, often the slow solutions that we come up with have been made faster by other people who have solved similar problems. And so Googling or looking in textbooks or Stack Exchange or other code recipe sources are good places to look for pre-optimized solutions. Also parallelization. Maybe if you have multiple calculations that can be done at the same time on different parts of your data set, that's a way of speeding up your code. Okay. And then figuring out which parts of your code are the bottlenecks can be done with what are called profilers. And Eshin and Lucy both mentioned them. Jupyter Notebooks has a time it function, I think a profile function that allows you to profile your code. And then there's a PyCharm profiler that you kind of click a button and it tells you how long each line of your code took to run. And that's a good place to look for places to optimize. Okay. Has anyone heard of vectorizing? Yeah. Do you all already know what vectorizing is? No. Okay. So if you have a loop in your code, it can often be written a different way as matrix operations. And it's tricky to do this. But in Python, there's a really nice kind of formalism called list comprehensions. And then there are also these functions called lambda functions and map. And these can be used in conjunction to apply a particular function to many elements of a list, for example, all in one line. If you can't think of how to vectorize your code, then you can try Googling a solution and seeing if someone else has come up with it. But one example of vectorizing is like if you have an array that you want to apply a function to, well, this is a silly example because it'll just do an analysis on an array of all zeros. But suppose you filled in this with data, and you want to apply some function to each element of the list. The kind of naive approach would be to loop through each element. There's a kind of vectorized way is to use map. And the syntax is you apply the particular function to each value of x, and then this converts it to a list, and this converts it to a NumPy array. And then here's the list comprehension version of that, where you apply my function to each element of x, and this is a kind of list index. Anyways, happy to talk through this stuff if you haven't seen list comprehensions or lambda functions or maps before. But they're often useful ways of speeding up your code. Okay. And finally, once you've done your tool or your coding, it's time to share it. If your code is on GitHub, everything's clean and well organized. You've got your tests. You've documented your use cases. You've selected a license. Your co-authors approve release. And to select a license, you should basically choose the MIT license. Or if you have thoughts on it, then it's probably you might have your preferred license. But here's a link to some details of the different license options. But the MIT license is probably right for you. Okay. You know what? You know how to document. Okay. Then it's time to release your code. So you can announce it through Twitter. Talk to, that's always a favorite. Make a poster, paper, talk, write a blog post. That's a really good way of getting users. Organize like a summer school, if you will, or a hackathon. Or just like tell your friends, like your former mentors, other people you've worked with or you currently work with, other people in your department, and that's a great way to build a community. Okay, so take-home messages. Hacking, which is what we'll mainly do this week, is about getting a minimum viable product, not necessarily about producing perfect code. But once you leave this week and go out into the world, things to think about are simplicity. That's really important. Keep your code simple, modular, etc. Think about use cases through storyboards. And remember funneling, early failing, and modular design. OK, thanks. Cool. Any other questions? All right, let's eat.